Hey, hey, hey. Okay, good afternoon. Welcome to Problem Set Discussion. Um, I hope that everyone is already here. Maybe we will wait like 1 minute. Okay, so let's start. So welcome to presentation of solutions of today's problem set. I hope that all of you enjoyed problem set and all the contest. And I will not speak too long because we are 10 minutes late. So I will just pass the word to our judges who prepared the problem set and solutions. So actually the first presented problem is Bob in Wonderland. So
Okay, so this was the easiest problem in the problem set. Basically, what were you asked to do was to find the minimal number of edge reconnections to make a path from a tree. You can easily see that we need to get rid of all degrees larger than 2. And we can also see that there is an easy procedure to do so. Just disconnect an edge and connect it to some leaf in the other component, which always exists. And what's the catch? The catch is that we don't have to simulate this process. So this boils down to just counting the number of reconnections, which is the sum of degrees higher than 2 minus 2. And the target complexity was linear. So really an easy task.
Okay, so another task was light emitting Hindenburg. It was about searching for, I think, k numbers from an array, and the task was to find such numbers that their end will be maximal. So we had an observation, really easy one, that if we achieve to persist a higher bit in the final end, then whatever we do on a lower bit, it could never be the better. So we could greedily go or iterate from the higher bits and check whether it is possible to persist the bit in the final end. And to do this, we just checked all the numbers which were remaining and checked whether there are at least k of them which had the bit. And in case of yes, then we have chosen all such numbers which had the bit on, and in case of no, we just continued. And we had such set, and we were iterating and reducing it, and finally we could obtain such number from the set which persisted. So the complexity is n log maximum, because there were log maximum iteration, and each of them was over the whole array. So it was this problem. Okay, the next problem is ABB. The task in this problem was to push minimum number of letters to the back of the string to make the string palindromic. In fact, there is a easy observation that this resulting string would look like a reversed prefix, some palindromic suffix, and some prefix, palindromic suffix, and reversed prefix. So we wanted to find out the longest palindromic suffix of the string, which could be done by a simple iteration over the string, and while using particularly any string matching algorithm, we checked whether the rest of whether the suffix is actually palindromic. So you could use a hashing or zeta function or basically anything, and here linear time was achievable, for example, by the zeta function. So this was about this problem. Well, okay. So another problem was Zelda in Garden, which was about to find the sum of divisor function on a range. Well, there is a easy observation, then we don't have to search it on a range, but we could search it from 1 to n and just subtract the the lower range, the lower bound from the upper bound. So we just had to find out how to solve this simpler problem. So firstly, let us have a Q, which is, there is a mistake. It shall be squared n, sqrt(n). So basically we iterated to squared n, but like to the lower bound, and took n divided by the thing we are iterating with, and we made it like twice. First one should be the numbers which always divide, or it actually says how many numbers are divided by the number e, and the second part would be like their mirror, because for now we would say all the numbers we are dividing with would be lesser than the squared, and their pair would be over the squared. So there would be like twice this sum. But yes, as you can see, we made a little mistake by this, and it was because we counted some pairs, and it was those pairs which were lesser, in which both the numbers were lesser than the squared n. So we basically just subtracted the squared, the second power of the square, or the floor of the square, and this just included all the combination in which we made mistakes. So basically, this is the formula for the answer, and the complexity is the squared n. Okay, so I don't know what is this. It's also mine, or? Yes, yeah.
So this was the problem where you got two strings over alphabet with 4 letters, and you want to turn the first string into the second one by swaps of pairs of letters. Yeah. So first observation is that all we need to know is like how many times a letter wants to be moved to another letter. Like here, letter C wants to be moved to letter A and C 8 times. So we built a graph on 4 vertices, and now another important observation is that a swap is a 2-cycle, and a 3-cycle or triangle can be composed of 2 swaps, and 4-cycle is 3 swaps. So every cycle. And now when we decompose this graph into cycles, 2, 3, and 4 cycles, then we get a list of swaps, and every cycle saves us 1 swap. And now the question is how to decompose this graph with multi-edges into the largest number of cycles. And the answer is, in this case, it is possible to do it greedily. Start with 2 cycles, take as many 2 cycles as possible, then 3 cycles, again greedily, take 3 cycles, and what remains can be covered by 4 cycles. And the complexity is linear. The main question is, why does the greedy work? So first, why can we cover 2 cycles? So let's assume that taking a 2 cycle was a mistake, so there was a better solution, and in this better solution, the 2 opposite edges of the 2 cycle were covered by 2 different cycles, but then we can transform this solution into a solution with at least as many cycles. Possibly we sometimes create more than 2 cycles, but always at least 2. So it's always better to cover 2 cycles. 3 cycles, now when we got rid of all 2 cycles, we have, it's like not so hard, but but you have to draw a few pictures to find out that actually there's only one case up to isomorphism. And in this case, there are only 2 directed 3 cycles, and now we want to find as many total number of C cycles here, but there's a simple formula in the multiplicities of edges, and it's easy to see that greedily taking like arbitrary of the 2 triangles as long as we can is optimal. So that's it.
Okay. Yeah, it's chocolate. Yeah. Okay, so basically we had another game in which we had a chocolate, and we had a move to crack the chocolate somewhere and eat 1/2 of it, which we have chosen, and there were some of the coordinates on the chocolate were, I think, poisoned or something like that, and we had to compete against some AI or well. So firstly, we can observe that we can divide this problem into 4 slightly independent problems or 4 games, because as you can see, if I eat the chocolate from right, it could never reduce the chocolate from top or from bottom, and there is always at least one poisoned piece, so we cannot reduce the chocolate from left. So these games are really independent, and we can also see that in fact these are NIM games when you can take any number of rows or columns from any side, and well, that's basically it. And here we want to firstly decide the state, whether it's winnable or not, which is easily done by XORing the 4 numbers, as you could see from the NIM theory. And if the XOR is equal to 0, then the state is lost, so we start with pass. Okay, the second part of it was to actually interact with the AI, so we had not only to decide whether the state is winnable, but we also had to decide how to move. But well, it was actually easy too, because we just had to find out how many rows or columns do we have to eat to make the XOR to be equal to 0. So basically we just tried it for all 4 sides, and it could be proven that for at least one side we could find such number. So well, that's basically it, and we had to iterate. There could be up to n moves, so basically the complexity is linear, and for each move it is constant. So like this. Okay, it's yours, I guess.
So in Deep 8080, the task was to find a circle with given radius, with center on a line, which contains the maximum number of points which we were given. So the first observation is that we can reverse this problem and basically shrink the cycle into a point and make all the other points into cycles of that given radius. And now we are looking for a point on the line which is in the intersection of the maximum number of these cycles. We were guaranteed that if we increase the radius a little bit, the solution doesn't change, so we do this. We add 1e minus 2 or something like that, and project the intersections of, or create the intersections of the line with the circles. Now, these intersections should be sorted and labeled by whether they start a circle or end the circle. We then iterate over these, add 1 when the circle starts, subtract 1 if the circle ends, and we just keep the maximum over the value. And that's the answer. So the complexity is by sorting. That's it.
Okay, so another task is Sabaton. In graph terminology, we were asked for each induced subgraph to count the number of components that we achieve. If we were to try the naive solution for this bound, or we would receive a quadratic solution. But we can notice that for these bounds, the total number of edges that we try among all queries is at most n times square root of n. And that is because the worst case is if we ask for a clique in each query. But there is an important, you can see an important thing, that although the number of edges in the graph is bounded by n if we set m to the maximal number, so therefore we can't, the maximum number of edges we can achieve is with clique of size square root of n, and there can be at most square root of n such queries. Therefore we decompose the problem into two cases, and whether we have a query of size m which is greater than square root of n, we go through all of the edges and check whether they are in the given set. And if we have the case when the query size is less or equal to the square root of n, we check all pairs of vertices and check whether there is an edge between them in the original graph. As we can see, as we move farther from the square root of n, we get even better bounds on the number of edges we have to try. But in the worst case it's n times square root of n. And the only last question is to somehow in the second step check whether the edge was in the original graph, and it was sufficient to use some standard set implementation in logarithmic time. So that was basically it. The only thing that we need to do after this is to count the connected component, which is an easy thing and which is linear in the size of the graph, in the total size of the graphs that we get in the queries. So the target time or target complexity was n times square root of n times logarithm of n. But we noticed that many of you came up with an even better solution that was faster by the factor of the logarithm. These were nice solutions that somehow reduced the size of the graph, but this complexity was sufficient, so everything with this should have passed.
Okay, so the next task was key equal to s, and we just had to find the number of strings of some length n, which do not contain strings from the input. So, well, firstly there is some slight observation, but it was not really necessary, just that there are two ways how to achieve it. Either to find the number of the strings which have some of the substrings, or which don't have the substring. So basically it was up to you which of these solutions you have chosen. So basically we had to find a way how to build the string, either one of them either with or without the substrings, and it could be shown that a sufficient way how to do this was equal to the automaton which was made by a Korasik algorithm, but yeah, the lengths were up to 100, so we could have used much worse algorithms. It's just to show how the automaton looked like. So basically this was about the way how to build the graph and how to do the states, and if the n would be smaller, we could have used simple dynamic programming, and whose complexity would be n times the number of states, which was like the sum of the lengths. But the n was pretty big, so we had to exchange the dynamic programming method. And well, one of the methods how to do this was by matrix exponentiation, when we build a matrix with the transitions and we multiplied it on n, and we, for example, could have exchanged the final state to one state with h to itself. Oh, thank you. And so basically by the combination of building such automaton and then metric exponentiation, it was possible to achieve complexity of L on 3, okay, it's cube, and times log n, where the L is the number of states in the automaton, so basically the length of the sum of the lengths of the strings. So okay, so the next problem was BGX, which was about we had an array on input, and for each subarray of it, we had to find the product of GCD times maximum on the array, and well, we wanted the sum of this in some modulo. So basically we had multiple approaches. One of the approaches was to do some divide and conquer over the whole array, when we had some range on which we wanted to find the answer, and we found, for example, the maximum on the range. So basically all the answers, and then we have found the all the subarrays which were passing through the maximum. And here we could see how what's the behavior of GCD, that it drops logarithmically. So there were only logarithmic number of blocks which achieved some GCD on the right part from the maximum, and the same for the left part. So we have searched for the boundaries of the blocks, and then for each combination we could have easily counted the GCD. So basically for each combination of such blocks, we added GCD times the maximum times the number of such subarrays. Then we divided the subarray to the left side of the maximum and to the right side of the maximum, and we continued by this process. So, well, okay, I skipped something. And so basically the complexity was somehow like n log cubic log max, because there were, as I said, maximum of logarithm number of blocks to the right side of the maximum, same thing to the left side of the maximum, and well, we also had to take the GCD, which I included in this complexity, which has also logarithmic complexity. So, well, that was about this. And another problem was problem of bugs, where the task was to find 1, 2, 3 patterns in a array, and we wanted only normalized patterns. So basically, if we don't normalize the patterns, there are 27 of them. Like it's we can choose any number on any position, but if we observe a closer look, there are only 13 patterns after this normalization. And it's even better because if we have an operation reverse the array and reverse the number, like the values, then we have only 5 patterns which are not isomorphic, which are these 5. And basically we can easily solve, or I hope easily, solve these 5 things. The first one could be solved by simple frequency array, because we could sweep the array and check for each number whether it was included at least 3 times, where 1, 2, 3 is similar, or for example we could take a minimum of prefix, maximum in suffix, and check whether this works or something like that. For 1, 1, 2 combination we could use also the frequency of the array and maximum. So we sweep the maximum from left and the frequency, also maximum from right, frequency from left, and checked for each the middle one whether there are the 2 things around it. The next 2 things were slightly harder. Well, for this one there could be used, for example, some data structure, and which could check the maximum on a subsequent or subarray between first and last occurrence of some number. And the last thing could be, for example, done by a combination of searching for a minimum on a prefix and by searching the highest number, which is lesser than my number in the suffix, which could be done, for example, by some set or something like that. So this was like n log n, and well, that's all to this task. So.
And the last task was named after the feeling you get when you are trying to solve it. The task was to compute a path length. You are given a polygon which describes a building, a roof of a building. The roof has slopes according to the nearest edge. So, for example, looking from top, we got the left image, and we are trying to compute the path going from the bottom to the top in this way. The path was always straight from the start to the end. Now, the real case, how it looks, is on the right, and you are trying to sum all these segments together. So one way to do this is similar to Voronoi diagram. You can build something like that and get the 3D model and basically compute the path, which is pretty hard. So there are some observations to be made to make it easier. One thing is that going through a site which is pointed to the north or to the south, the length you walk is multiplied by some constant according to the angle you are walking in. So this can divide the path into three parts. So one is going through the north-south part of the roof, another is going through the east-west part of the roof, and the last one is going outside the roof. So the goal is to compute the points which divide the path into these parts. And one simple observation is that, of course, we compute the line intersection of our path with each edge. So that's a possible point of interest. Another point of interest is whenever two lines next to each other can create this ridge. So we have a line in 45 degrees to it, so that's another possible point of interest. And there is also another one. Well, basically for each pair of sides, one horizontal, one vertical, there's a possibility that these two parts of the roof meet somewhere, so this line is also a point of interest. For each of these points, we can compute the type of a roof which we will travel on. We sum these lengths and multiply it by respective constants. The solution is n cubed because we have n squared points of interest, and for each one we will compute in linear time the type of the roof segment which is ahead of it. So this is our presentation of solutions. Thank you for your attention.
Okay, so thank you for really nice presentation. So it's time now for questions. So, okay.
What's going on about task K? It was a reject or no? What is the situation?
Yes. Just to clarify on this, in K equals problem, actually we realized that there is some error in test data. So basically now we are rejudging all the submissions. So, but we don't know the results yet for sure. So actually it will be announced on the official announcement in Bethlehem Chapel. Okay.
What are you going to do with that? About wasted time or accepted, and how are you going to change the result?
Actually, I am saying it's now under investigation, so it's not decided yet, right? So actually at the official announcement. Okay. Any other question?
Can we hope that accepted submissions to K equal S would gain 20 minutes penalty even if they would be accepted in the final score, because these teams would gain this penalty even if they would instantly correct their solutions.
Yeah, that's actually that's the part of that decision. So actually, I said the decision was not made yet. So please be patient and wait on official announcement in Bethlehemská kaple. Okay.
Out of curiosity, what was the type of the error? Whether your outputs were wrong or were possibly some strings on the input were longer than you promised? Was like input or the output wrong?
Yeah, actually maybe it would be better to ask the author of or guys who were solving that, but actually there was no problem on input. Okay, so no problem on input. Input was correct. So any other questions? So we are really very sorry that this happened actually. So, but we had more solutions for that k equals, and they were created independently, and they were all they provided all the same results. So we believe that it is correct. So I'm really sorry for judge team. So and for you for sure.
So have you discovered this problem during the contest or only after? Because, like, for example, our team asked if you are sure about the tests.
We discovered this problem like 20 minutes before the contest finishes. So really late to do something what can help you. So are there any other questions? Okay, so, but I think despite of that all problems were really wonderful, and actually you can imagine that it is really tough work to prepare all these difficult problems. So I would like to say thank you to all judges for this magnificent effort. Actually, it is not like 10-minute task to create that problem. So thank you so much to all of you. Okay, so if there are no other questions, we can finish this session now. And the continuation is, or announcement of results is in Bethlehem Chapel at 6:30. I hope it is written in a program you received. So now it's a free time for you. So thank you so much. See you there.